Howdy physics folks. Today I'm coming at you remotely. Today we're going to be talking about center of mass. Normally I would show you a bunch of in-class demos that relate to this topic, but since I'm not here today, you get to hear the recorded version. So anyway, here we go. I would traditionally set up two carts on a track and ask you, well, if there was just one cart, where would the center of mass of that cart be? And everybody would go, oh yeah, it's in the middle of that one cart. But what if you have two carts? Say I have one cart at 70 and the other cart at 130. Where's the center of mass of both carts? And the answer, of course, is halfway in between at 100. Okay, so that's how we figure out where the center of mass of two equal objects is. You basically just look at them and say, oh, it's right there. Well, what happens if the objects are moving? What if one of the objects is moving this way and the other one's object's moving the other way at the same speed? Guess what? Is the center of mass moving? No. Why not? Well, because one's moving one way, one's moving the other way. And if you think about it, the center of mass is always going to be halfway in between, and that halfway in between spot isn't moving. Likewise, if they're moving it apart at the same speed, that halfway in between spot is also not moving. So in either case, the velocity of the center of mass is zero. So what does that mean? It's basically, we've got this principle is, say you have a collision. Two cars coming at each other, they hit, they bounce off, and they go away from each other. What was the velocity of the center of mass before the collision? Zero. After the collision? Still zero. Hey, guess what? That means there's this general principle that says the velocity of the center of mass before and after a collision of a system of masses is equal. Which is kind of another way of thinking about Newton's first law, which says that there is inertia. The whole system, the two carts themselves have an inertia, which basically is stationary. And then, well, afterwards, the two carts, even they're moving away from each other, still have a system-wide inertia, which is still stationary. Why? Because there's no external forces on them. And that is another statement of Newton's first law, the law of inertia. What if you want to calculate the center of mass of two stationary carts of an equal mass? Well, that's easy. All you have to do is, if you got m and you got 2m, well, the center of mass is going to be a little bit closer to the 2m than to the 1m. In fact, if you think about it, it's going to be 1/3 from this side and 2/3 from this side, because it should be a 2-to-1 ratio, right? Because the mass is 2-to-1, therefore maybe the center of mass, distance from the center of mass, should also be 2-to-1 ratio. And if you have a 2-to-1 ratio of this distance to this distance, what you're really talking about is dividing this entire distance between them into thirds and saying 1/3, 2/3. So if the total distance d is d, then the center of mass is 1/3 from this side and 2/3 from that side. Alright, and then you can do a little math, and let's say this one's at 50 centimeters and this one's at 100 centimeters, 150 centimeters. That means that the location of the center of mass is 1/3 the way to here, which is 83.33 centimeters. Alright, moving on. We're going to generalize what we just said and say, well, if you got two objects, the x position of the center of mass is the x position of the first object times the mass of the first object plus the x position of the second object times the mass of the second object divided by the total mass. So in this case above, you've got, let's see, that's 2m times 50 centimeters, that's here, plus m times 150 centimeters, that's here. See, 2m times 50, that's 100m, and then that's 150m. Let's see, so 100 plus 150, that's 250m on top. And then on bottom, you've got the total m's over over 3m. So 250m over 3m is, I don't know, the m's cancel, and it's 250 over 3, which just so happens to be 83.3 centimeters. That's kind of neat. Well, if you take the derivative with respect to time of this and this, you're just going to get, sorry, of this here, you're just going to get velocity. So the velocity of the center mass is v1m plus v2m over m1 plus m2. That's kind of cool. What if you wanted to generalize this? Could you see the pattern? Of course you could. All you have to do is, if you had three masses, it's x1 m1 plus x2 m2 plus x3 m3 all over m1 plus m2 plus m3. And in summation notation it looks like that. Summation of all the xm's divided by the summation of all the m's. Same thing with velocity. Alright, so that's what you do if you want to know the center of mass of an arbitrary number of particles. Alright, so moving on. What about, well, what if you could move in 2 dimensions? Let's say you had 2 pucks colliding, and we're talking air hockey pucks, so there's no friction at all. Let's see, here's one of the pucks, here's the other pucks. They come at each other. Boom, and then they collide. Sorry, my fingers need to be able to come closer together in order to do this properly, and then they go out. That's kind of neat. If you think about it, if these 2 pucks have equal mass, at time 1 the center mass is here, time 2 the center mass is here, time 3 the center mass is here, time 4 the center mass is here, time 5 the center mass is here. What did the center mass do? Hey, look at that. Straight line, steady speed. That's a constant velocity. Guess what? Collisions do not affect the velocity of the center of mass. Wait, didn't we just write that down somewhere? Oh yeah, we did earlier. Up here. Here we go. Newton's first law holds not just for single particles but also for systems of particles. The velocity of the center of mass before the collision equals the velocity of center of mass after the collision. Wow, that's awesome. It works in 2 dimensions as well. Alright, so moving on. Let's see, what if, instead of just letting these 2 things bounce off each other, what if we apply an external force to one of the particles after the collision? Let's say to this guy. We're going to apply a force. What happens? Well, you get something like that. After the collision is, after the force is applied, right here, this mass goes off in a different direction. What happens to the center of mass? It can't be tracking along in the same direction because there was an external force applied. Huh, that's neat. Let's move on. Fireworks, one of my favorite things. Why? Because you can tell all the nerds in the crowd who are tracking the center of mass of the firework. Because guess what? The center of mass of the firework is going to behave exactly the same before and after the explosion. So what you can actually do is you can track all the fireworks going up in a big parabola, and you can see the exploding center of mass, the center of the mass of the explosion. If you take all these particles that have exploded, you'll see that they just continue on, and if you track all the exploding bits and pieces, you'll see that the center of mass of all of that is still the original parabola. Alright? It's pretty cool. So you'll see all the nerds in the crowd with their fingers up in the air, tracking the parabola as the fireworks explodes, and I think that's awesome. Fireworks are great. Alright, next thing. What if, instead of having a single particle, or sorry, 2 particles or 3 particles, what if you have a continuous mass distribution? For example, let's say you had a meter stick. Where's the center of mass of the meter stick? Well, of course, it's at the halfway point, right? Prove it. What? How do you do that? Well, let's think about it this way. As a simple example, let's say you had a little bit of meter stick over here. So wouldn't that be counterbalanced by a bit of meter stick over there? Yep. And what about a bit of meter stick over there? That'd be counterbalanced by that bit. And that bit is counterbalanced by that bit, and so on. And every single bit is counterbalanced such that the center of mass of this guy is right in the middle. Alright, great. But we all know that since it's a uniform mass distribution, we have to use some calculus to deal with that. So, here it is. The position of the center of mass, instead of having a summation sign on top for x times m, and a summation on bottom for for all the m's, what we do is we say, well, it's the total mass, which is just big M on bottom instead of just little m1 plus little m2 plus little m3. And on top, instead of a summation sign, we use an integral and do little m dx. And little m is mass as a function of position, and dx is your tiny little piece of position all along the stick. Kind of cool. Alright, so here we go. Let's apply it. Whew. If you assume, and this is a big assumption, if you assume that the meter stick has a uniform mass distribution, what does that mean? What that means is for this particular meter stick, every centimeter of the meter stick has the same mass density as every other centimeter of the meter stick. And because it's all the same mass density, we know that the entire mass density along the length of the meter stick is just the total mass divided by the total length. And it's constant for every little bit. So what we're going to do is make a statement that looks like this. The mass density per length of every little piece of dx is dm. And that ratio of dm per dx is the same everywhere along the meter stick. And it's not only that, it's the same as the entire mass divided by the entire length. Alright, that's a very important thing. What that means is you can relate the mass dm of a little piece to the length dx of that little piece. Alright, that quantity, dm over dx, by the way, is called linear density, which you'll see in some problems. But usually we just write dm over dx. Alright, but here's the real kicker. Wow, I got a little sloppy. My notes should say something like this. Dm equals capital M, which is the entire mass, over capital L, which is the entire length, times dx. Alright, that's kind of cool. Okay. See, what was our original equation here? Our original statement. M dx, right? Well, I didn't actually need to do that. Oh well. I'll just keep it then. I made it a little bit more complicated than it needed to be. Oh well. Let's step back a little bit and let's just say what the heck? I have a typo in here. Should be the integral of mass dx. Let's change that here. Alright, let's rewrite that. Should be m dx. Alright, is that what I had up above? Yeah, m dx, okay. So m dx, and m is m over L times x dx. Alright? And so, what can we do? We can pull m and L are both constants. They're just the mass and the length of the stick. Pull those out. Alright, and you're left with just x dx, and you're going to integrate x from 0 to L. The m's cancel, of course. the mass of the stick doesn't affect the location of its center of mass, which is just 50 centimeters. So we integrate, we get 1/2 x squared from 0 to L over L. You do all that, and you get, well, one of them cancels out, and you're just left with 1/2 L squared over L. Well, the L's cancel, one of the L's cancel, and you're just left with 1/2 L. Guess what? The location of the center of mass of a meter stick is L over 2, which is 50 centimeters. Great! That's what we predicted, just from common sense. What if it was a little bit more complicated than that? Well, then say you had a meter stick that was skinny. Let's see, let's draw that. What if you had a meter stick that was shaped like that? Where's the center of mass? I don't know. Probably like right there. Well, how would you find it? Well, go through the same process. But instead of having a constant linear density, you'd have a changing linear density that changed with x, and you'd have to integrate it, and it'd be a different integral, and etc., and you'd end up probably with a center of mass of about right here. Alright, that's nice. Let's move on. Let's say, this is where it gets fun. Let's say that you had a meter stick, but you wanted to know the center, the two-dimensional center of mass. Well, that's really easy. If you lay a meter stick along the x-axis, it's right there at the 0.5 meters in the x direction and 0 meters in the y direction. All right. Well, let's do 2 half-meter sticks. Well, then that's fairly straightforward too. You can tell it by symmetry. What you do is you figure out where the center mass of this guy is, which is 1/4 meter in the y direction, and the center mass of this guy, which is also 1/4 meter in the y direction. So if the center mass of this one is here and the center mass of this one is here, the combined center mass of the two of them has to lie along that line somewhere. And, well, guess what? Because they're the same mass, it's halfway. Well, that's kind of common sense too. What if you had one full meter stick along the bottom and 2 half-meter sticks? So what you do is, well, we know from before that the center mass of the 2 half-meter sticks is right here, and the center mass of the full meter stick is right here. And how much mass is here? Well, a full meter stick's worth. And how much mass is here? Well, because it's 2 halves, is a full m here. So you got 1 m here and 1 m here. So the combined center of mass of both of them is 2m right there at the 0.125 meter mark in the y direction and 1 meter in the x direction. That's pretty cool. You didn't do any special math to do that. You just kind of looked at the meter sticks. All right, let's do another one. Oh, nope, that's it. I guess that's the whole lecture. You guys missed the actual meter stick demo with it. For that, I apologize. Hopefully I'll be back in person in 2 weeks. Hope you enjoyed the lecture. If you have any questions, send me an email. Thanks. Bye.